Today we go back to the late 19th and early 20th century to talk a little bit about the model of the atom given to us by J.J. Thomson and how we surpassed it. Thomson saw the atom as a kind of a plum pudding, or that's what he used. In the U.S. we'd probably talk about a raisin pudding. The electrons were embedded in a sphere of positive electricity, and that's how the electrons could rub off, and that's how the atoms could bond together through the plus-minus attraction. Now, electrons are very light. If they're embedded in the sphere of positive electricity, they're not going to provide any particular obstacle. And in fact, nothing in the sphere of positive electricity is very dense. It's a fairly uniform, if not homogeneous, looking atom. The Thomson atom is. So, we would think that if we would shoot a positively charged projectile at the Thomson atom, it'll maybe deflect a little bit, or it'll go straight through it. So Thomson is predicting, as this animation shows, that there will be little or no deflection if you shoot positive particles at this sphere. Well, Ernest Rutherford, in 1911, tested the model. Alpha particles had been discovered with radioactivity. They're positively charged, they showed that, and they're not particularly heavy. They're certainly heavier than electrons. They are ions, that is, positively charged particles, and radium and certain other elements will give them off. So what Rutherford did was he collimated them, that is, he kind of projected a narrow beam of them, and he shot it at a very, very thin film of gold, just a few atoms thick. Gold, of course, is a very dense element. Thomson would predict that if any of the alpha particles get through, they would go straight to the target. And the target was cadmium sulfide, which will scintillate, will give off sparks-looking results when ions hit it. Indeed, most of the positive particles were undeflected. The great majority did. The scintillations were generally dead on, right in the center of the target. Yet a significant number of flashes were seen above and below the center line, and Rutherford found that some of them even, well, they were detectable behind the foil. He said it's as if you'd fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Because remember, the gold foil was very, very thin. So he reasoned that since most of the alpha particles went straight through, there was not a lot in there, not a lot in the volume that was dense, but that there was a part of the atom that was very dense. The atom's mass then is not evenly distributed throughout it as Thomson thought, but rather concentrated, positively charged, because the alpha particles, which are positively charged, were repelled by this massive, tiny volume of the atom. He called this concentration of mass and charge the nucleus, and he named it after the nucleus of the biological cell, and found that it is less than 0.1% of the volume of the atom. It's an extremely small part of the atom. So, if you wish, Rutherford's atom, because the electrons have to stay outside the nucleus, Rutherford's atom was constructed with the electrons revolving about the nucleus like planets around the sun. This is a model of the helium atom, with 2 electrons circulating around the nucleus. Now, Rutherford's problem was he didn't know how it was that the electrons could orbit the nucleus, because we know that accelerating charged particles lose energy. Electrons are constantly accelerating towards the nucleus. Therefore, they would spiral into the nucleus if they were revolving about the nucleus. According to classical physics, Rutherford's atom could not hold up. It would collapse. However, Rutherford advanced our understanding of the atom because he notated that the nucleus is the locus, the place where the atom's mass, 99.9% of the mass of the atom, is in this nucleus, and he also showed that all of the positive charge of the atom was in the nucleus. The electrons then are left outside as the engines for all chemical reactions. We say, for instance, that all chemistry is electron chemistry. Rutherford gave us, for good or bad, what we call the nuclear age. Chadwick in 1932 made his contribution. If you consider oxygen, the atomic mass of oxygen is 16 AMUs, but its atomic number, the number of protons, is 8 AMUs. What, he would ask, makes up the difference? There is a difference in mass, but not in atomic charge. And through a very, very clever experiment, he found the neutron. The neutron has a mass of 1 AMU, but it has a charge of 0. This leads us to the notion of isotopes. The neutron's function appears to be to help hold the nucleus together. Remember, you've got a lot of positive charge concentrated in a very small volume. The existence of the neutron, then, establishes forces that keep the nucleus together. All atoms that have more than 1 proton, that is, all atoms with atomic number greater than 1, have at least 1 neutron. Now, 2 atoms of the same element will always have the same number of protons, but they can differ in the number of neutrons. Carbon, for instance, has 3 isotopes. Their chemistry is exactly the same. Carbon 12, carbon 13, carbon 14. We can separate these with a mass spectrograph. Isotopes of the same element then have the same chemistry. They have the same reactions, they have the same physical and chemical properties. The only difference is their mass. Isotopes of the same element then differ in mass, so they have different numbers of neutrons. Isotopes of the same element have, again, different masses, but the same chemistry. What we see on the periodic table and any other element mass chart is a combination of all isotope masses. That's what we read on the periodic table. We'll go into more of that next time when we talk more about isotopes. How do we separate isotopes? Can we separate them chemically? Well, think about that. Their chemistry is the same. What is the physical difference? Well, now you know, it's their mass. So, if we put them in a centrifuge, we could separate them by mass. It would take a while, and we'd have to have several repetitions of the centrifugation. But if we could find something that doesn't dissolve in water, we could slurry it up, put it in a centrifuge tube, and then the more massive isotope would come out first. This is used to purify isotopes of uranium to get the stuff that fissions, that is, that can be used in a nuclear reactor, or, unfortunately, a nuclear weapon. The mass spectrograph is also used to separate isotopes. We charge the isotopes, we accelerate them inside a magnetic field, and then the more massive ones, being slower, will not turn as fast as the lighter isotopes. This is a picture or a diagram of a mass spectrograph. And as you can see, we ionize all of the isotopes. We accelerate them. They are charged. And as they go into the magnetic field, they start to turn. As you can see, the slower isotopes will go up here, and the lighter isotopes will go there. And so down here in the detection, we'll get the heavier isotopes over on this side of the screen and the lighter isotopes over here. This is going to be a very useful tool that you'll study more in the AP Chemistry class.